Hello everybody. So today's topic, soil morphology. And so what is soil morphology? Well, we want to pick right up on this idea of the soil physical properties that we left off on. So we came up with the ways that we can find differences in the soil by looking at their physical properties and seeing how, structurally one soil will be different from the other, or how texturally the soil will be different from the other, or the idea that it's all sand, silt, and clay, but just in different percentages. And so then what soil morphology is the idea that we're now going to look at those physical properties, we're going to observe them, and we're going to describe them. So we're going to now try and see those in the soil and see where we can see the differences, and then that's going to help us describe the soil even more. And so if we take that down to a basic level, so if we look at any place where we're looking at soil, our basic soil unit is going to be a pedon, which is this hexagonal column all the way from the top, which is the surface, all the way down to the bedrock. And if you have a bunch of pedons together, that would be a polypedon, where you got many pedons in an area. And a polypedon is when we would put together like a soil map, that would be your basic mapping unit. Soil profile, when we come up with a soil profile, or we've looked at soil profiles, what we're really just looking at is one face of a pedon, one face of a pedon, whether it's here or here or here. We're just going to look at the changes in the soil within that one face. And then so within a soil profile, you have horizons, and horizons are just the different layers within that soil profile. So if I pick one specific face here, which is right here, we can see that there's a layer here, another layer there, another layer there, another layer there, and then we're down into the bedrock. And so that's what we're really kind of talking about today. We're just going to try and see how we would describe this, describe a pedon and a soil profile, and all the different terminology we can come up with. So let's take a look. So in order to describe our horizons, our different soil layers, they've come up with a coding system. So it's a number, a capital letter, lowercase letter, and then a number. Now, not every layer is going to need all four of those. Some of them might use all four of them. Some of them might only use three of them or two of them. But it just kind of depends on what is present in that layer, because we're trying to be as specific as we can without being as complicated as we can. And so the first number would represent the sequence of parent material if there's more than one. So what does that mean? It means that if it formed from two different parent materials, like you had a natural process that's happened for a long amount of time, and then something else happened as well, that you get soil forming from two different parent materials, then that number would represent the different parent materials. Usually, though, that's not a super common thing, so you don't really see that first number in a lot of soils. Usually, the first thing you see is a capital letter, which we can see here in this example right here, where we see the O, A, E, B, C for these different layers. The lowercase letters that then follow the capital letters are going to indicate specific characteristics of the master horizon. So our capital letters here, those are our master horizons. In this one specifically, we've got our organic layer, our topsoil layer, our leaching layer, our subsoil, and our parent material, and we'll go over all those in detail. But then there'd be lowercase letters after it. One that's common is you can see an AP for your topsoil, and that just means that it's a layer that's been plowed. After the lowercase letters, you could then have numbers again, which would be subdivisions of the horizon. So if there's some sort of a reason to say that this part of the horizon is different from this part of the horizon, but it's not a completely different horizon, then we would use the number system to separate those. We'll kind of show some examples and do our best to kind of make that understandable. So what we'll do is we'll take a look at at a typical grassland soil, but we're also going to throw a forest soil in there just to kind of give us a look at the soil profile and the different master horizons and why they're different. So the first one we'll start off with is the organic layer, which is at the top. Now the organic layer is not always at the top, so the way I like to describe this to people, to hopefully not get them confused, is that this order that we see them in with the horizons, the O, A, B, C, R, for this typical grassland soil, that's the order that it has to be in if all those layers are present. However, you don't have to have all those layers present. What do I mean by that? Well, you don't have to have an O layer. For example, if it's a desert soil, you don't have an O layer. Why? Because there's not a lot of stuff in the desert to create that surface litter that then becomes humus, that then works its way into the topsoil. So you don't really have an O layer in the desert. So it would just start A, B, C, R, and go from there. Or down in the Kern River, there is no A layer or a B layer. It starts off as a C layer. And so you start off right at C, down at the parent material, because it's been formed by alluvium, so stuff is constantly washing in and out. So you don't really have any topsoil or subsoil development, because when the water's flowing, all that stuff just kind of washes away. And so that's the way to kind of think about it, that there is an order to these things, but not every layer has to be there every single time. And so if we're starting off here at the organic layer, we're actually talking about the surface litter, and the organic material that's working its way down from the top. That's why the next layer is going to be called the topsoil, even though we've got this organic layer over the top of it, because the topsoil is the top of the soil working its way up, because everything started as rock down there in bedrock, then it became weathered bedrock, which is that C layer, then it became soil that became layer after layer after layer after layer until we got to the topsoil, and then the organic layer is the stuff from the surface that's working its way down into the soil. So the organic layer is on top, taking things from the surface and bringing them into the soil, and then our next layer is our topsoil, which is the top of the soil working its way up from the bedrock. So the topsoil is usually darker in color, and that signifies a richness of accumulated organic matter and minerals. And also, if your soil is nice and healthy and everything's going right, your soil should go from darker to lighter as you go along, because you have this greater presence of organic matter and minerals, because it's working its way from the surface down, and eventually you're just going to have less and less as it works its way through the soil. Usually the topsoil has a granular texture, and nutrients will be leached into the deeper layers, but a lot of it's going to get used up there in the topsoil. That's why the topsoil is so rich. That's why we plant, and most of the roots and everything is just in the topsoil, and it doesn't really go a lot deeper than that, because that's where basically the topsoil provides the plant with everything that it needs. So definitely a high presence of plant roots. Soils that are higher in organic matter are usually darker in color and will have a greater water holding capacity. That's one of the great things about high amounts of organic matter, is they can hold on to water really well, which is great. If we see lighter colored soils, less organic matter, less water holding capacity. So here's where we switch into a forest soil, and I'm going to move myself over here so that I'm not, oops, there we go, that's better. So move myself out of the way so you can see the picture clearly. So if it's a forest horizon, more than likely, it's not totally common, it doesn't have to be there everywhere, but it's more common in a forest soil than it is in a grassland soil, where we get this E horizon right here, which is a light colored zone, where there's been a bunch of eluviation and leaching happening, and it's it's E for alluviation, or for which leaching and alluviation really mean the same thing. One of the big things that's important to understand about an E horizon if it's there, is that the reason it's got that light color to it is because the organic matter and the minerals, that stuff from the topsoil has worked its way down, but it has leached through that layer. So the next layer below is actually going to be a little bit darker than this one, because all that's going to be left in this E horizon are all the minerals that didn't get leached through, and so those are going to be of usually of a lighter color. Usually an E layer, if it's found, is found in the forest due to the presence of fungi in the forest, as opposed to grassland soils are more bacteria dominated in terms of microorganisms. Just to go over it again, leaching is the process in which soluble nutrients are lost from the soil due to precipitation or irrigation, or really in this case lost from one layer of the soil to the next one. Like I said before, the E layer is not seen in every single forest layer, but you could see it there, and it's usually pretty distinct because it's got that light color to it, and it just goes from dark to light and then back to a darker color again. Alright, move myself back up here and out of the way. So then that takes us to the subsoil. So looking at this diagram on the right, so if this was a forest soil, we would have gone OAE, BCR, but we're looking at a grassland soil, so it's just OABCR. So now we're at B right here, which is the subsoil. So you can see we'll still get some plant roots present, but much less than we're in our A layer or our topsoil layer. And we're going to get a lighter colored soil because the nutrients have leached out of the topsoil. They have accumulated in the B horizon, but there's definitely not as many, and then there's definitely not that high presence of organic matter, which really gives us that much darker color. The B horizon is typically rich in iron compounds, soluble salts, aluminum compounds, and clay. And those, because of those, the presence of those minerals and those compounds in the soil, you're going to get a much lighter color as well. And especially with the iron compounds, because they're easily oxidized, that you're going to get a lighter color, kind of a rust color in some places. Our next layer down is our parent material. So our parent material is the C horizon. Sometimes they'll just say weathered bedrock. And all we're saying is that the C horizon used to be the R horizon, which all the soil used to be down there in the R horizon. But instead of this consolidated rock, the unweathered solid bedrock, in the C layer, we have weathered bedrock. So it's been through water or wind erosion or water and air processes, the rocks has broken up into different pieces, and those different pieces then are just sitting there. And then what's interesting about that is we usually don't get plant roots going that deep, but then that's now where our groundwater storage usually will happen. The sea horizon is often the one that's going to be saturated with groundwater if you have an underground aquifer below you. That's where it's going to form. And then that takes us to the last layer, which is the bedrock. The rocks that are typically found in bedrock, things like limestone, quartzite, sandstone, basalt, granite. Granite is the one in the Sierra Nevadas down here. That's usually our parent material for the southern Sierra Nevadas. So that's the bedrock for that area, and we know that because there's big pieces of it sticking out of the ground, like El Capitan. In areas where the bedrock is exposed at the surface of the ground, these materials will weather. So the El Capitan, Half Dome, those big pieces of granite sticking out in Yosemite won't look exactly the same as the granite that's under the ground because that the unweathered bedrock hasn't gone through that weathering process. If the bedrock gets exposed, it should weather away and eventually years and years and years kind of become like a sea horizon where we could start to build soil, that sort of thing. Why won't that process happen at Half Dome or El Capitan, it could happen, but the way that they're exposed to weather, to wind and water erosion, it's not likely that you're going to get enough time for soil to build up with that constant wind and water erosion happening. Some people don't look at this as a horizon because it's not technically soil. It's everything before soil, but it is our foundation that our soil builds upon. So it's important to know. Also, one way to think about, we just talked about the sea layer, and why does the sea layer have groundwater in it? It's because all the soil we know has pores where water and air move through, but eventually it'll hit the unweathered bedrock. It'll hit the bottom where now there's nowhere for it to go. So now it puddles up and pools up, and that's how we could start to build a groundwater supply. So those were our master horizons, O, A, E, B, C, R. Those are our master horizons: the organic layer, the topsoil, the alluviation layer or the leaching layer, the subsoil, the parent material layer, and then the bedrock. And then we also have these lowercase letter distinctions, which are trying to tell us something specific about our master horizon. And so, an example, so if we see something where the lowercase a is used, and it's usually, it tells you right here, it's used with the O to indicate the most highly decomposed organic materials in organic soils. Or if we look at something that you'll see come up sometimes, and probably not great depending on what you're trying to do with the soil, is C for concretions. It says C indicates a significant accumulation of concretions and non-concretions if the non-concretions are cemented with material other than silica, iron, aluminum, or manganese. D would also be another one that you'd want to know about, but you wouldn't be too happy about it. D is for physical root restriction. So it's for root restricting layers in naturally occurring or man-made unconsolidated sediments or materials. G, strong glaying. G means that the predominant color of the horizon has a chroma of 2 or less because of iron being reduced and removed due to wetness or saturation with the water. You can see these kind of go on, you know, H for alluvial accumulation, I for slightly decomposed organic material. There's more than this. This is just kind of some examples that I got for you. R for weathered or soft bedrock. So R is used with C to indicate layers of soft bedrock. So you would see R being used with C. You wouldn't really see it used, the lowercase r, with any layers other than C. We talked about P before, because I said you could have an AP layer, which is a topsoil that's been plowed or some other disturbance by cultivation or pasturing. M for cementation. You got V would be plinthite, so V is used to indicate the presence of iron-rich, humus-poor, reddish material that is firm or very firm when moist, and that hardens irreversibly when exposed to the atmosphere. So that's an interesting one. X for frangipane character. X indicates genetically developed firmness, brittleness, or high bulk density. So there's a few examples of what the specific characterization that the lowercase letter is trying to make of that master horizon. So let's take a look. So here's kind of our basic grassland soil, our O, A, B, C, R layers, and where they start. So this is in inches. So right up here at the top, we've got our O layer, and we've got our O layer, and then we go down and we have our A layer here. So we can see a little change in color. So you can see right here at the top, you've got your O layer, real dark color there. We get to our A layer where we also have a darker color, but not anywhere near as dark as that O layer at the top. We then get down to our B layer, our subsoil, and you can see that this, we've got the depletion of organic matter because we don't have that brown or that dark brown color that we see up above, but we also see an accumulation of clay, and clay is typically iron and aluminum-based compounds in it, and we can see that that is more than likely true because of this bright reddish-orange color that we see in our B layer. We then see our C layer down here, where we see our parent material or our weathered rock material, and then you can see down here where we actually hit the hard bedrock and the unweathered bedrock. Another look at it. So in this soil profile here, which is up in Santa Clara County, so we've got our O horizon up top, way up top here. We then have our A horizon. We've got a B horizon, a subsoil. We get our C horizon, which is, this is a really good look at a C horizon to me, because you can see that there's still the soil and all the soil development up above, but then you can also see the big pieces of weathered bedrock, and how it used to be the part of the bedrock, but now it is weathered into much smaller pieces. And then we've got our bedrock feature down below. Let me go back one. There we go. So here's another look. I'm gonna kind of move myself, do my best to get myself out of the way here, just so you can see the pictures. So right here we start off with an AP layer, so that's topsoil that's been plowed or cultivated or changed in some way like that. We then go to an E layer, where that's that leaching layer that we have here. So if we didn't know anything about it, we'd probably assume that the soil might be forested with trees or shrubs up above, just because that's much more common to think. So we can see that our E layer, it's a little bit lighter in color, and then when we go down below, we can see it actually darkens back up again as compared to the lighter color here in this E layer. We then have a B layer for our subsoil, and a C layer where we get to our weathered bedrock. I'll move myself out of the way now. If you want to read, or you can pause and read how they describe this soil from southern Michigan. And it's just the big thing with morphology, and the big thing with what we're doing today is really trying to get you to just see these differences, and just to start to be able to look at soil and say, well, wait, that looks different from that, and how are we going to classify that, and how are we going to say that this is different from that? Because it obviously, with our eyes, we can see it, and we can see that difference, but how do we actually express it, or how do we make it so that everybody else who sees this same distinction can understand it and classify it in the same way? Here, I'll move myself to the middle here. And so kind of looking at the same thing here, a couple different ways to look at it. So here we got, here's our surface, and then our surface litter at the top. We've got our A layer here, our topsoil, a nice dark topsoil. We definitely have a really obvious E layer here, an alleviation, a leaching layer here, and then we've got a B layer, and it's a BT layer. So then we see that strong leaching layer that leads to this BT. T is the idea of an accumulation of silicate clays. So that's what that T stands for there on the right. On the left here, you see another one of these AP layers. So that's our topsoil that's been plowed or cultivated in some way. We see BW, and W stands for a change in the B layer due to or some sort of a change in color or structure. We see here that this one, so it says 2EBG. So the 2 here, we talked about that at the beginning. It's not totally common, but it does happen, where it means that there were 2 different parent materials. So there was some process that happened, and then some other process that happened. So there's 2 different parent materials within this soil, and then this is an E and a B layer combined with a B, and then there's a B layer down below, and then the G, the lowercase g, that means glaying, and then we can see the T again here, so that's that accumulation of silicate clays, and the glaying as well. And I'm not going to, pretend that you're going to memorize all these things and it's all going to come to you right away, but there's lots of glossaries and lots of field manuals and things that'll have a list of this, and once you figure it out and you know what you're kind of looking at, then you can just look it up and say, oh, okay, it's, there's a G here, I know I can look on the list, G means glaying. What's glaying again? Oh yeah, this is what it means. And that's kind of the process. But as long as we have a lot of these descriptors in place and we can use them and we start making what our eyes see match up to what the description is, that's when we're off and running and everything's golden in terms of really trying to get a good description of a soil profile here. So just kind of going over some of the stuff from before, right? Soil pedon, if we, cut a perfect hexagonal shape out of that, but we're looking at one face of that pedon, so this whole thing is a profile. Then we've got our horizons within the profile, all of our different layers within that profile. And then we've got master horizons, these capital letters, your A, B, E, B, and B here. We've got our lowercase letters, which are specific designations or specific characteristics about that master horizon. If we have a number before the master horizon, that means that it's there's more than one parent material. And then if we had a number after the lowercase letter, then there's subdivisions within the horizon. So I'll move myself back up here to the top right out of the way. And so just a little kind of quick quiz right here on our basic layers of a grassland soil, our O horizon, our A horizon, our B horizon, our C horizon. So go ahead and look at this, read the descriptions that I have there in 1, 2, 3, and 4, and then I want you to pick of these down below of the orders that I put down there, which order is the correct if we're going to describe top to bottom the O layer, A layer, B layer, and C layer. So go ahead and pause the video. Alright, so did you guess that one? 3, 4, 1, 2. So if we're describing the O layer, a thin layer of decomposing organic material, our A layer has fine absorbing roots of trees and is very biologically active, and that this layer is normally rich in organic matter. Our B layer then has fine textured materials from the horizon above, the things that leach down, and soil particles from the lower parent material, right? The B horizon sitting right above that parent material. And then number 2, partially weathered parent material, that's the description of our C horizon. So other ways that we're going to describe the soil or focus on describing a soil profile. We focus on the color. So using the Munsell color charts, that's the most common way of doing it. They focus on 3 values, which are the hue, the value, and the chroma. The hue is your dominant spectral color or your color of the rainbow, the ones that we focus on using in class. They'll say YR after them, and YR stands for yellow-red, and that's how we get our brownish colors that we see a lot in soils. It is some sort of combination of yellow and red, or somewhere in between. So that's our dominant spectral color. Our value is going to be the lightness or darkness of the chip, or the soil that we're looking at, the lightness or darkness of it, and then the chroma is the purity of the color. So how pure is the color, or what else is in that color that makes it lighter or darker, or not as rich, more dull, not as rich, sort of a thing is the way that I would look at it. Because if we're saying value is lightness or darkness, then chroma, I would say, is kind of the richness of the color. And why is color important? Well, we know that most soil minerals are colorless. So if soil is gray, there's not going to be any organic matter in it, and and it's gonna be kind of obvious color-wise that way. If the color of the soil is black or brown or reddish color, there's something else going on, something else happening there, and that's an important distinction that we can make, and that's why it's important in terms of a morphological description. We also can use texture. The field test is the one that we're big on, and one of the big focus points on the field test is being able to ribbon correctly between your index finger and your thumb, and the longer the ribbon you can make, the more clay you have in your soil. And so you start to get a feel for what does sand feel like, what does clay feel like, and then silt as well. Structure, the size and the shapes of the PEDs within your soil profile and how they were distinctly formed is going to tell us a lot about the soil profile and give us a lot of good information. We're also going to look at the strength of the soil, which is also called the consistency of the soil. So it can vary from loose to cemented, and it's really going to depend a lot on moisture content. And the way to estimate that is just how easy is it to break the soil apart. Can you use your fingers? Do you have to use your hands together to break it apart? Do you have to put it under the foot and stomp it to be able to break the soil apart? Or does it not break apart doing any of those sorts of things? We also have reaction, which is a measure of the relative acidity or alkalinity of the soil, which is going to be based on your soil pH. And your soil pH is going to determine your nutrient availability in the soils. So your soil pH is measured on a scale of 0 to 14. 7 is neutral, so that's where water is. Water is neutral. It's neither acidic nor alkaline. Soils with pH of less than 7 are acidic soils. Soils with pH greater than 7 are alkaline soils. And here's just kind of a look. Soil pH of 6 to 6.5 is really perfect for tree growth, but you can see based on these minerals here, and that's what's important to us, is our nutrients and how many nutrients are available and where can we get them. You can see anywhere between 6 and 8 we're probably decent, down to 5.5 maybe even we're okay. Anything there is pretty good, but anything outside of that starts to become problematic. And I'm going to slide myself over here now because I want to just talk about this a little bit right here. When soil is acidic, minerals such as iron and manganese, so if we find down here, here's iron and manganese right here, they dissolve in soil water. So it's good if the soil is slightly acidic. It's going to be really easy to get iron and manganese. In small quantities, iron and manganese are going to help your plant grow. However, if your soil gets too acidic, down below 4 or so, then iron and manganese just start to accumulate and accumulate and accumulate so much that they can actually harm or kill your plant. And the same thing can happen with other nutrients on the more alkaline side. That once you get to a point, you get too much accumulation on some of your more alkaline soils, that also becomes a problem. It's Goldilocks theory, right? Not too much this way, not too much that way. You know, in the middle is just right, sort of a thing. And our last big morphological description that we're going to talk about is drainage. Drainage is going to depend on soil permeability. So how quickly and easily does the water move through the soil? The slope position, because it's going to be really important. Are we top of the slope where everything's going to be expected to be, running downhill and you're going to get a lot of runoff issues? Are we mid-slope? Are we at the bottom like we are here in Bakersfield? We're in a valley, so we get a lot of things accumulating down at us, and then amount of precipitation. And so when we're talking about drainage, we're really talking about the depth and duration of a high water table and where the water table is. Now, the water table is just the top of where the groundwater is in the soil. And so when we're talking about drainage, we kind of got three basic categories. So we got uniformly brownish or reddish subsoil. So it's not saturated with water very often, and you've got good aeration. You can have a mottled soil, which is like a mixed brownish gray. That indicates that the water table will fluctuate during the year. So where you can find groundwater, instead of it being here all the time, maybe sometimes it's up here, maybe sometimes the water's down here. So maybe I have to dig, during the winter, I don't have to dig that far to get water. But during the summer, and there's a lot less water available, maybe I've got to dig a lot farther. And then there's uniformly gray, which means it's going to be saturated with water for a few months a year. And drainage is super important when we're talking about crop selection, when we're talking about trying to identify wetland areas and what are certain types of wetlands, like what's an ephemeral wetland or what's a more permanent wetland. Suitability for on-site waste disposal, if that was something if we were trying to accomplish, because it's going to be important to know how wet the soil is and how water moves through the soil. So just giving you, we'll go into detail more when we talk about soil-water relationships, but just to give you an idea of a water table. So all we're saying when we're saying the water table is the top of wherever the water is within the soil. And so if we see something like a river or a lake, all that means is the water table is above where the ground is, and that's why the water pools up on top of the ground. And so in a lot of places, what you'll see is you'll have a higher winter water table than you will in a summer water table, because you have usually, especially out here in the western United States, and especially in California, we get wet winters and we get dry summers. And so you'll usually see a much higher water table. It'll be much easier to dig and get to water in the winter than it will in the summer. And then, of course, down below here is where we've got our groundwater, and then up above here is our unsaturated zone, or our vadose zone. And the reason that is unsaturated is because we've got plants and we've got soil and we've got all these things that are actually using the water. And so then whatever water doesn't get used up there permeates through the soil, percolates and infiltrates, and then ends up down here in the aquifer as stored groundwater. So here's kind of a look, because we've been talking about this whole thing before. Here's our soil profile. We can see there's definitely different colors going on in here. So we've got a plowed surface horizon. That's an AP, or it's our topsoil that's been plowed. We can see down here we've got a BW. So we've got that changing of color happening, and it's our subsoil. And then we can see down here that we've hit water. So that's the water table. So if we were trying to figure out the depth of the water table, we would just measure until we got to here, and that would tell us where the start of our water is within the ground. And that's what I got in terms of morphological description. So I hope you enjoyed that, and we'll just kind of continue on from there.